Lesson on collision theory. Collision theory says that a reaction may occur only after an effective, we're talking about what effective means, collision. Only a very small number of collisions are effective. There are two factors on whether a collision is effective or not. One factor is energy. They must collide with enough energy, and this is related to the temperature. The higher the temperature, the higher energy, the faster the particles are going. What you do is you need enough energy to overcome the activation energy. The activation energy is the minimum amount of energy needed to break the bonds of the old molecule. Minimum amount of energy to break bonds. And or bring the particles together if it's ionic. In a reaction diagram, which you are going to have to do, your basic reaction diagram for an exothermic reaction, you have the reactants, and here you have the products. Now looking at this chart, you think that boom, it goes downhill, but you must overcome an activation energy. Each reaction has its own unique amount of activation energy needed to proceed. So the height of this hill, and this is energy versus time, that is the activation energy, abbreviated AE. At the top of this is the transition state. Transition state, abbreviated TS. So if you have reactants occurring right here, you have a particle that looks like this, plus a molecule that looks like this. And then if you have a transition state, that's when they all come together into one super particle. And then it rearranges to make the products, which is making chemical reactions. You got to produce something new. So yeah, something like that. Now at this point right here in the transition state, even though they all are aligned, half the time they'll fall back to the reaction side. Only half the time they'll fall back there. So there's a limitation on how many particles can react. First of all, if they don't have enough energy, they won't overcome. If there's not enough energy, the particles aren't moving fast enough, they won't go high up the hill. They won't reach the transition state. Even if they do hit the transition state, some will fall back, some will fall forward. So this is the activation energy there, and this is the change in energy, or the energy of the reaction itself. You can say this is 10 kilojoules, and this is, looks like maybe 20 kilojoules. If you reverse the reaction, you're starting with the product level, and you go up here, and you end up at the reactants level. But now, instead of going up 20 kilojoules from your starting point, you got to go up 30 kilojoules. So there's a greater jump. And then the delta E energy of the reaction is positive. because you're going uphill. Here it's a negative. Activation energy is always positive. This is a simplified energy diagram. In real life, if you have a series of steps, just like we did in the last lesson on reaction mechanism, you can have step 1 be slow, or be fast, step 2 be slow, and step 3 be fast. In this case, the slowest step is the rate determining step. It also has the highest activation energy. So it doesn't proceed in one jump like these reactions do. First, you have a products. It'll go up to a lower level. It'll come back down some amount, some higher level, some lower level, and then it'll go up higher. And the second step is the slowest step, so that's the highest hill. And it might go down here someplace and on down. The activation energy overall is the height of the tallest peak. But if you notice here, there are not one, but 3 transition states. And at the bottom point here, you could be forming reaction intermediates. Remember, reaction intermediates are something that's formed and then used up right away. So the activation energy here is this amount, the height of the tallest peak. Now, in real life, this peak and this peak doesn't really matter, so you can simplify it down to a one hump where the slowest step is the activation energy. When you raise, one way of looking at the energy, if you have the particles moving faster, let's say at this reaction right here, if your energy is higher, let's do this reaction right here, your energy starts higher, instead of being at this level, which represents a certain temperature, you'd be at this level. So if you have a higher temperature, your starting point's higher, so it requires less energy to go over the hill. The activation energy shrinks with the increased background energy, and therefore more particles have enough energy to go over the hump, and the reaction is faster. So this is at a low temperature, this is a higher temperature. So one factor, the main factor is energy. The other one is orientation, especially if you have a molecule. Orientation. Molecular reactions generally, not always, but as a rule, they occur slower because they have to hit in a certain spot. Let's say you have this molecule here, and in order for a reaction to occur, it has to hit right here. It's like a baseball. You hit the sweet spot. If you hit it here, it has enough energy to break apart the two things and rearrange. If it hits it here or here, it'll just move it around, or it'll spin, or something like that. So only a very small percentage of the actual collisions occur, even if they have enough energy. Even if this has more energy, if it doesn't occur in the right location, it won't work. Now, if you have an ionic compound, there's no place, it's just a charge, so any location can go. So generally, ionic reactions occur faster because there's no appreciable orientation factor. There's still that 50% might fall high, might fall forward, might fall backwards. So the speed of the reaction, or the rate constant, bringing two things together, is experimentally found to be A, which is the Arrhenius factor, E is the natural log, EA, activation energy, RT. This is the rate constant. We've seen that before. This is the orientation part. And this is the energy part, or the temperature. Since you have E, if you know anything about natural logs, you can take the natural log of both sides, and you end up with, if you know anything about it, if not, just trust me, the natural log of K is equal to negative the activation energy R, rearrange things slightly, 1 over T, T's in Kelvin, plus natural log of A. This corresponds, like we did in last lesson, y equals mx plus b. So if you graph this, this is the natural log of K. This is the temp. This would be natural log of A. Actually, it's 1 over temperature, not T, but 1 over the temperature. It's a negative slope, so it's going downhill. And the slope, m, is equal to negative EA over R. And this is the basis behind how you find out what the energy, activation energy is for a reaction. The R in this case, since we're talking about energy, R is equal to not the gas law constant, but the energy constant, joules, Kelvin, moles. Okay. So what they do is, in a lab situation, they experimentally find out what the activation energy is. You do a lab at 2 different temperatures. You get the natural log of the second temperature, negative EA RT2 plus natural log of A. And then you do it at a lower temperature, natural log K1, because a different temperature has a different constant, negative EA RT1 plus natural log of A, which is a constant. If you subtract these 2 equations, you get the natural log of K2 minus the natural log of K1 equals, the natural log of A's cancel, and since you're minusing, let's put the positive term first. Positive EA RT1, because that's positive, minus a negative is a positive, minus EA RT2, factor out, combine natural logs and factor out a temperature, and you get the equation that you'll see on some of the homework problems. The natural log of K2 over K1 equals negative EA over R, 1 over T1, because these are opposites, 2 and 1 are opposites, on the equation that you use. And this is the equation because you can find out the rate constants by what we did last time at the 2 different temperatures of the experimental control. R is a constant, so this way you can calculate what the activation energy is. So this is how EA is calculated from lab data. That ends this lesson on collision theory.